So in this example, we're going to determine the internal shear and moment of a simple beam with a single point load. In order to do this, the first thing we're going to need is the reactions. So as always, we always want to start by kind of estimating what we think some of the answers are going to be, but also with free body diagram. So on the right here, I've redrawn the beam, the load, and the geometry, and because we have a roller on the right, we get a vertical reaction. We'll call that RB in the y direction, and on the left we get a vertical reaction, RA in the y direction, and a horizontal reaction, RA in the x direction. And we need to solve for these three unknowns before we can do the shear and moment diagrams. We could do this by proportion because the 90 kip load is at the 1/3 point, and because there's no horizontal reactions, we could immediately say RAX is equal to 0, RAY is equal to 2/3 of 90 kips, which is 60 kips, and RBY is 1/3 of 90 kips, or 30 kips. To be more rigorous, we can use our equations of equilibrium, and you'll see you'll get the same answers. We could say the sum of the forces in the x direction equals 0, to the right being positive, equals, and all we have in that equation is RAX. So you can see how RAX is equal to 0. Again, we could do the sum of the forces next in the vertical direction or the sum of the moments. Because we have two vertical unknowns, I'm going to go to sum of the moments. So sum of the moments, and I'm going to pick point A here because it has the most unknowns, counterclockwise being positive. Those moments have to equal 0. And to be explicit, we get RAX times 0 feet plus RAY times 0 feet. And again, you can leave those out as you get more comfortable with these equations, but I like to make sure I account for everything. So I'm going to show those. Then we get a 90 kips times 10 feet. And because that is going in a clockwise sense around point A, we get a negative in front of that. And then we get RBY, and that's 30 feet away. And because that force is around point A is going counterclockwise, counterclockwise being positive, we get a positive in front of that. And so you can see here, because this equation equals 0, we get the same result. We get RBY is equal to 90 kips times 10 feet over 30 feet, which is equal to 1/3 of 90, or 30 kips. Finally, we can take our sum of our forces in the y direction equal to 0, and we'll call up positive. And in this case, we get RAY, we get RBY, both of them positive because they're both pointing up, and we get minus 90 kips. We just found that RBY was 30 kips, so we can immediately conclude that RAY is equal to 90 kips minus 30 kips is equal to 60 kips, which is what we found up here. So we have our reactions. Now if we look at the semi-graphical method for solving shear and moment diagrams, we have a few things we need to look at. First of all, we start from left to right, and when we have a reaction, the shear at the left end is going to equal the left end reaction. So let's go ahead and draw out our shear diagram first. And when I draw these diagrams out, I'm going to draw a black line here horizontally, and I drop down blue lines just as guidelines. So we'll start with shear. The shear at our point A is going to equal the reaction at A, which is 60 kips. So I'm going to go up about 60 here. So I go up to 60. So this is 60 kips. Now the change in shear between 2 points, so if I'm looking at the points here, I'm going from point A to point the point of the load, the change in shear is equal to the area of the load diagram. Well, in this case, I have no load diagram, and so the change in shear from here to here will be 0. So I draw a horizontal line straight over to that point. Now, so I stay at 60 kips. Now, at a point load, we get an abrupt change in shear equal to the magnitude of the point load. So in this case, we have 90 kips going down. So I'm going to go down 90 kips here. So that's 90 kips going down. And that takes me down to a minus 30 kips. Okay. And once again, because the change in shear between 2 points, now we're looking here to here, the change in shear is equal to the area of the load diagram. Since I have 0 load, I will have 0 change in shear, and it runs straight across at minus 30. And then I have an abrupt change at the other end, RBY, which is equal to 30 kips, so I go up 30 kips. So this diagram here is my shear diagram. And you can see how we should end up at the far right end with the same value as our right end reaction. So that's a little bit of a check. Next, we're going to look at the moment diagram. The moment diagram here because we start off with a pin, because the left end is a pin right there and the right end is a pin, we know that our moment at the ends is going to be 0. So we know the moment at this point is going to be 0 and the moment at this point is going to be 0. We also know the maximum moment happens where the shear diagram crosses the axis. So at this point right here is where we're going to have our maximum moment. There's a few observations we have from the semi-graphical method. So let's go ahead and do some computations. Again, the change in moment between 2 points, so we're going to look at the change from here to here, or here to here, is equal to the area of the shear diagram. So all we need to do is find the area of this rectangle right here. So the area of that rectangle is going to be 60 kips times 10 feet, which is equal to 600 kip feet. The slope of the moment diagram is equal to the magnitude of the shear diagram. So when we go from 0 at this point up to a moment of 600, okay, the question is how do we get there? Do we go in a straight line? Does it curve up? Does it curve down? Not sure which way it goes. So let's look at the shear diagram. Since the shear is 60 at the left end, we start off with a slope of 60, continue with a slope of 60 till we get to the end with a slope of 60. So when the shear is horizontal, we get a moment diagram that's just a straight line between the 2 points up to 600 kip feet. Okay. Now, on the other side, we have a shear of minus 30 kips. So minus 30 kips for a distance of 20 feet, that tells us that the change in moment, so the change from here going this direction, is equal to the area of this guy. So let's go ahead and calculate the area of that. The area is equal to minus 30 kips times 20 feet, which is equal to minus 600 kip feet. So I start at 600, I subtract 600, and I get down to 0. So my moment drops down to 0. And that's the nice thing about this method is it checks out. I get 0 kip feet at the pinned ends. It's a straight line because we have a constant slope of minus 30. So this is the moment diagram for a point load. And a few things you can look at here. First of all, when you have just point loads, your shear diagram will have a bunch of horizontal lines like this. and there'll be different numbers depending on how many point loads, and the moment diagrams will have slope lines like that. So let's take this to the next example, and let's do a uniform load. Same beam, but let's go ahead and throw 2 kips per foot on the beam, and let's see what that moment diagram looks like. So again, for a uniform load, the first thing we need to do is find our reactions. So it's helpful to have a free body diagram. And we use resultants to find reactions, but you need to be cautioned that when we're doing shear and moment diagrams, the only time you can use a resultant is for the reactions. We have to leave the load in its shape that it's shown to do the shear and moment diagrams. And I'll do an example later showing, comparing what it would look like if we actually left it, in the resultants. So let's go ahead and find the reactions. You can probably guess here that since we have a total load of 60 kips on the beam and it's uniform, we're going to get an equal reaction on either end. But let's go ahead and draw this up. So the resultant is 2 kips per foot times 30 feet, which is equal to 60 kips, and that will be located 15 feet from each end. We get a vertical reaction on the left, a vertical reaction on the right. Again, it's 15 feet on both sides. And we get a horizontal reaction here. And I'm showing this because if there were much more loads, it might not be obvious what the solution is. So let's go through and do it. Sum of the forces in the x direction equals 0 equals RAX. So RAX is equal to 0. Sum of the moments about point A, counterclockwise being positive, equals 0, equals, and I'm not going to show the one RAX and RAY because they have lever arms of 0. I'm just going to go directly to the 60 kips times 15 feet, and that'll be a negative, again because it's going clockwise around point A, and RBY of course is going to go the other direction, so it'll be a positive. So I get RBY times 30 feet, because 30 feet is the distance from A, and when we solve this we get RBY is equal to 15 over 30 times 60 kips, which is 30 kips, which we expected. Sum of the forces in the y direction equals 0, up being positive. We get RAY plus RBY minus 60 kips. Of course, that gives us RAY is equal to 60 kips minus 30 kips is equal to 30 kips, which we expected as well. So we have our reactions at the two ends. Now, again, I need to emphasize that using this resultant can only be done for our reactions. We have to go back to our original diagram to do the shear and moment. So let's go ahead and use our semi-graphical method to solve for the shear and moment diagrams. So let's start at point A, and at point A the reaction is 30 kips, so we're going to go up 30 kips. Okay. Now, we need to know what the change in shear from point A to point B is going to equal the area of the moment diagram, of the load diagram, I'm sorry. So the load diagram has an area equal to 2 kips per foot times 30 feet, so it's just the area of this rectangle, and it's pointing down, so it's a negative, so minus 60 kips. So the change in shear from point A all the way over to point B, so from here to here, is going to be a minus 60. So 30 minus 60 gives us minus 30. Now the question is, how do we go between the two? Does it go as a straight line or a curved line? Well, the slope of the moment diagram is always equal to the magnitude of the load diagram. So right at the beginning here, our magnitude of the load diagram is minus 2 kips. So we go in as a slope of minus 2, and it's a constant slope of minus 2. So what we end up with is a shear diagram that looks like that. So if we go over 5 feet, we drop down 10 kips. We go over another 5 feet, we drop down another 5 kips. It's 10 kips, etc. And what we end up with is we're crossing, by the time we've moved over 15 feet, 15 times 2 is 30, we've dropped down to 0. So our shear is 0 at 15 feet over, and it's always important to note where this happens, because we'll need that for the moment diagram. For the moment diagrams, again, because we have a pin at each end, the moment starts at 0. The moment will be maximum where the shear crosses the axis, so at 15 feet over. And so we can calculate the change in moment is equal to the area of the shear diagram. So the area here, A, is equal to 1/2 times 15 feet times 30 kips, and that gives us 225 kip feet. Okay, and down here we're going to need this one as well. A is equal to minus 30 kips times 15 feet over 2, which results in a minus 225 kip feet. So our moment diagram starts at 0 and ends at a maximum of 225 kip feet. So we get a change in moment going up of 225. So it goes up 225 and then drops back down 225. The question is, how does it go? Does it go in a curved line, straight line? Is it curved like this? Does it go like that? It's difficult to tell until we look at the shear diagram. So let's look at the value of shear. The value of shear at the left end is 30 kips. That means the slope of the moment diagram at the left end is going to be 30 kips. So we go in with a slope of 30. And the slope at 15 feet is 0. So we have a slope of 0. And halfway over, our slope is going to be 15. And when we get to the end, our slope is a minus 30. So slope equals minus 30. So we're going to fit a curve where we start steep, and the slope gets shallower till we end up with a 0 slope, and then it drops off. So our maximum moment is 225. Our moment here is equal to 0, and our moment here is equal to 0. So this is the moment diagram. It's a nice smooth curve. And this is our shear diagram. Okay, so we have a shear diagram, moment diagram for a uniform load, which are 2 triangles and a parabola. And when we have a point load, we get these rectangles and triangles. So what happens if we put the two together? So let's go ahead and see what happens when we put 2 of them together. Now I'm going to spare you the details of coming up with the reactions here, but the reactions will just be the combination of the reactions from the previous 2 problems. So the horizontal reaction, of course, is 0 because we have no applied loads. The vertical reaction at A, so RAY, is going to equal 90 kips, and the vertical reaction at B is going to equal 60 kips. You can go ahead and show that to yourself, prove to yourself that that works out. So now we're going to use the same principles of semi-graphical method to come up with our shear and moment diagrams. Let's start out with shear. So if our reaction on the left side is 90, we're going to go up to 90. There's 90 kips. And we use V for shear and M for moment. So we go up at 90 kips. And what's going to happen is we're going to drop off at a rate of 2 kips per foot. So if we go out 10 feet, basically what we need to do is find the change in shear from here to here is going to be the area of the load diagram between those 2 points. So we have an area here, it's 10 feet long and 2 kips tall. So let's find the area of this. A equals 10 feet times 2 per foot, and it's a minus 2 kips, so it's minus 20 kips. So that means we drop off from there to there down to 70 kips. We drop from 90 to 70. Again, it's going to be a sloped line at a constant slope of -2. And then we get a abrupt drop in shear due to this 90 kip point load. So we're going to drop down the 90 kips. So let's go down 90. So 70 minus 90 takes us down to minus 20 kips. And then what's going to happen is we need the area of this diagram here. Well, the area of that diagram is minus 2 kips per foot times 20 feet is equal to minus 40 kips. So we start at -20 kips, and we're going to drop down to an additional 40 kips. So we drop an additional 40, so -20 minus 40 is minus 60 kips, and that brings us to our reaction at this end. Back up. So there's our shear diagram. We get the moment diagram by looking at the shear diagram. So again, because we have pins at both ends, our moment's going to start at 0. Where the shear diagram crosses the axis is where the moment's going to be the highest, so we're going to get a maximum moment there. And visualizing this, we're going to start off at a steep slope of a 90. We're going to come into this high point with a slope of 70. We're going to leave it with a slope of 20 and drop in here with a slope of minus 60. So let's go ahead and do this. Let's find the change in shear from here to here is going to be the area of this shear diagram. I'm sorry, the change in moment from here to here is the area of the shear diagram. So let's find the area here. A is going to equal 1/2 times 90 kips plus 70 kips divided by 10. And that gives us 800 kip feet. Note how the units are constant. We have, it's times 10 feet. So that's just the area of a trapezoid. And the area of this thing is going to be minus 20 kips minus 60 kips times 1/2 times 20 feet. And that turns out to be a minus 800 kip feet as well, which makes sense. So we're going to start off at a slope here, same as the shear, a slope of 90. We're going to go into our maximum point here with a slope of 70. So it's going to curve like this. And then we're going to come out with a shallow slope of 20 and end with a steep slope of 60. So it gets kind of a flatter curve over there. So there's a little bit of a point going on there. Again, our maximum moment is equal to 800 kip feet. So this is our moment diagram, and this is our shear diagram here. And we need to make sure we label all the points. So m equals 0 at the pins. Okay, and so just in review, what you can see here is the moment diagram of the combined loading looks similar to the combination of the other two. We get a uniform load, and if you were to just add these two point for point, you would get the actual same number. Notice how the maximum moment is different on both of these. It's 600 on one of them and 225 on the other one, and they happen at 10 feet and 15 feet, but the maximum moment combined happens at the 10 feet over. So you can't just add the two together. We can't just take the 225 and add it to the 600. We actually have to do it mathematically. So I'm going to complete this one here, and then I'm going to do another one after this one where I can show what happens if we tried to do the shear and moment diagram of this using the resultants.